In this lab, we will find the liquid susceptibility for the buildings which are um, around the Alpine Faults. We will continue with the data analysis of Alpine Faults. So first so for the building's data frame, I for loop for the building's geodata frame will take more than 10 minutes at 50 iterations per second. Even the alternate apply method will take a few minutes. To help speed this up, and so you are not sitting around waiting for it, if you need to rerun this function multiple times, we have pre-calculated this in the column liquid source for you. The function we ran was okay. So this function was ran. Now I will just I have done that beforehand, and I will show you what happens over here. So first we display first few lines of build and buildings data frame. In build data frame, we had buildings data frame, but with the MMI column created. And in the buildings data frame, we had, so this is the data frame buildings, and we also have MMI. Select buildings equal build, because that was build was most updated data frame of buildings data frame, and we display buildings data frame. So let's have a look. Okay, so now we use point query to find the liquefaction susceptibility at each nearest bridge. So point underscore query, open bracket, buildings, and double open square bracket, geometry, and this building's double square pair of brackets and geometry inside will create geometric column in a pandas data frame form, and we want the rows 200, comma TIF underscore path is the susceptibility liquefaction susceptibility, and no data equals 0, interpolate equal nearest. So we want to find nearest value of the liquefaction susceptibility of the geometry, which is located in row number 200, and we want the value, so we put 0 in the square bracket. But we will have this in array form, and there are 5 values of liquefaction susceptibility. So what happens is that the geometry in buildings data frame is multi-polygon, and each multi-polygon contains 4 polygons. So, and for each of those polygons, it takes 5 polygons, and for each of the polygon, the center point of it is taken and meshed with the TIF path to get the nearest liquefaction susceptibility. Okay, so we run that, and now what if we put geometry, same thing, but dot centroid. Dot centroid, what it does is that it finds the center of the multi-polygon, and then it finds the nearest liquefaction susceptibility for their center point, and that's 4. Use point query to find the liquefaction susceptibility at each building. So list of susceptibility equal empty array. For building geometry in buildings geometry column dot centroid, LQ underscore source equal point underscore query, open bracket, building underscore geometry, comma, TIF underscore path, comma, no data equals 0, comma, interpolate equal nearest, and then the value of it. And list of susceptibility dot append open bracket LQ underscore source. So let buildings, we create a new column in the buildings data frame, LQ underscore source equal list of susceptibility. Sampling the 10 data rows from the buildings data frame by passing the command buildings.sample open bracket 10 close bracket gives us this. And you can see that LQ susceptibility is over here, the column. Then we see the unique LQ values, and that they appear as type float 64 buildings, and the column LQ underscore source dot unique gives us these values 4351 and nan 02. Nan is the not applicable value. Split into known data and unknown data. Here we'll assume we need to replace LQ underscore source equals 0 as well. Known equal, so what happens, the known data frame is created from the values of LQ underscore source, not NA, and greater than 0. So buildings, and inside the square bracket we'll have the LQ underscore source dot NA, not NA, open and close bracket, and buildings, open square bracket, LQ underscore source greater than 0. Then we'll create unknown column in unknown data frame. In unknown data frame, we'll have the buildings data frame, and open bracket, open square bracket, and open bracket, buildings, the LQ underscore source is NA, open and close bracket, or buildings LQ underscore source equals 0. So display known dot head open and close bracket, and unknown dot head open and close bracket. So we get this. So this is for known data frame, and this is for unknown data frame. Find nearest unknown geometry of unknown geometry. So we'll pass the command temp equal known dot s index. Now s index will find all the indexes dot nearest open bracket unknown dot geometry, comma, retain underscore all equal false, close bracket, and this one over here, inside the pair of square bracket will make us choose second array, which is matching the unknown dot geometry, finding the nearest geometry in the known data frame. So the first array will be containing all the indexes of the known data frame, but the second array will contain the indexes which are near to this unknown geometry. Unknown, then we let unknown the column nearest known IDX equal to pandas.series, and open and close bracket. Inside we will have temp. Unknown.head will print the first few lines of the unknown data frame, and we see that nearest known IDX column is created with all the nearest row indexes from the known data frame. Drop LQ underscore source column in unknown data frame. Unknown dot drop open bracket, columns equal, bracket, LQ underscore sus, close bracket, comma, in place equal true, close bracket. Then check the row indexes in known data frame, known.ilog 12933, and the LQ underscore sus value is 4. So let's see. So we have 12933 and LQ sus value is in this known column. We have, okay. So, okay, so at the moment, the unknown data frame for contains no values for, okay, but known data frame has the value 4 for LQ sus value for the row index number 12933. Okay, so now we join to the known LQ underscore sus based on the row names. Unknown equal unknown dot reset underscore index drop equal true will help us not to create a new column with the old indexes. Dot join open bracket noun and this double bracket and the name of the column LQ underscore source. So this will help us to create a pandas data frame of containing LQ underscore source values. Dot reset underscore index bracket drop equal true. Now what happens over here is that it will reset the index and drop equal true will help us not to create the old index column. On equal nearest known IDX. So it takes this nearest known IDX, matches with finds joins to the this index numbers from nearest known IDX column um, and reads the LQ susceptibility values and creates a new column here. So for 12933 we can see LQ underscore sus is 4. Now drop nearest known IDX column. So we no longer need nearest known IDX column. So we will drop it in unknown column in unknown data frame. Unknown dot drop bracket square bracket nearest underscore known underscore IDX close bracket comma x is equal 1 comma in place equal true. Show calculation gpd dot geo data frame open bracket pandas dot concat open bracket open square bracket known comma unknown. So pandas concat known comma unknown. So known data frame will be put and then the unknown yeah after known column known rows and then comma ignore underscore index equal true. So ignoring the index, so which means the index will be in ascending order from 0 to reset from 0 to the end. And we'll convert that to geodata frame by putting gpd.geodata frame. Okay, so there are 47,108 rows and 11 data columns. Then we join the data frames back together using the pandas concat function. So I just have shown the calculation part of it. So we will just, so this one over here, this assigns, this command assigns that data frame that we create from unknown and unknown data frames to buildings. So buildings equal gpd.geodataFrame of pandas.concat square bracket known comma unknown close the bracket comma igno underscore index equal true. Then we build, so which means igno underscore index. Now buildings dot reset underscore index bracket drop equal true. Now this will make sure that the indexes are reset uh, and are in ascending order. Okay, now we see the unique LQ underscore sus values and that they appear as tab float 64. So display open bracket buildings dot LQ underscore sus dot unique open and close bracket display open bracket buildings dot LQ underscore sus dot data type and close bracket, and that gives 43512 nan and float 64. Check CRS, buildings.crs. Now we are using the coordinate system with the EPSG value 2193. Visualize LQ underscore sus for buildings. Background underscore map equals South Island dot plot. Bracket color equal light gray. Close bracket. Buildings dot plot. Open bracket. IX equal background underscore map. Comma. Column equal LQ underscore sus. Comma. Legend equal true. So we have this, and we can see that there is some dots are dark yellow, which means the LQ underscore sus for those buildings are value 5, and the light values and the dark blue values mean lowest LQ sus values. The values of LQ liquefaction susceptibility range from 1 to 5, and the color is from blue to yellow.